How does motor imagery work for BCIs? Imagine being able to control a computer or a robotic arm just by thinking about moving your hand or foot. It sounds like science fiction, but it is actually happening through brain-computer interfaces. When you think about moving your hand, your brain activates specific areas, especially in the motor and sensory parts of your brain. These areas send electrical signals that can be detected without any physical movement. This process is called motor imagery, where you mentally simulate a movement without actually doing it. In brain-computer interfaces that use motor imagery, sensors placed on your scalp, called electroencephalography or electrodes, pick up these electrical signals. The signals contain patterns that change depending on what movement you are imagining. For example, imagining moving your right hand creates a different pattern than imagining moving your left foot. These patterns are like unique signatures that the system can recognize. Once the signals are recorded, they go through a series of steps. First, the raw data is filtered to focus on specific frequency bands, usually between 8 and 30 Hz. This range includes brain waves called mu and beta rhythms, which are closely linked to movement. Then, advanced mathematical techniques analyze the signals to find features that distinguish different types of motor imagery. Some methods look at how signals from different parts of the brain relate to each other, helping to improve accuracy. Next, machine learning algorithms like support vector machines, convolutional neural networks, or long short-term memory networks analyze these features. They learn to classify whether the person is imagining moving their hand, foot, or other body parts. The better these algorithms get at recognizing patterns, the more precise the control becomes. People using motor imagery brain-computer interfaces often receive visual or virtual reality feedback. For example, a virtual hand might move on a screen when the person imagines moving their hand. This feedback helps users learn how to generate clearer signals and improve their control over time. Some systems also combine sensory inputs like touch or vibration to boost brain signals and make classification more reliable. Motor imagery brain-computer interfaces are especially helpful for people with paralysis or motor impairments. They give a way to communicate or operate devices without needing to move their muscles. While there are still challenges, like variability in signals between different people or sessions, ongoing research is making these systems more accurate and user-friendly. In essence, motor imagery works for brain-computer interfaces by tapping into the brain's natural ability to simulate movement internally. The brain's electrical activity during this mental rehearsal is captured, processed, and translated into commands that control external devices. This technology opens up new possibilities for restoring movement, aiding communication, and creating innovative ways for humans to interact with machines.